This is SpaceTime Series 19, Episode 91, for broadcast on the 21st of December 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the black hole ASASSN, a new search for Earth's unseen companions, and India caps off its biggest year so far in spaceflight. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A sudden unusually bright flash of light in a distant galaxy, which was thought to be the explosive death of a star as a supernova, has turned out to be an even more spectacular stellar death, namely the total destruction of a star by a supermassive black hole. A report in the first issue of the journal Nature Astronomy claims new observations indicate the unusually bright flash, which has been named ASASSN 15LH, and which was originally thought to be the brightest supernova ever seen, was actually a tidal disruption event caused by a star being ripped to pieces after venturing too close to a monstrous black hole. The new study, led by astronomers at Israel's Weizmann Institute for Science, is based on 10 months of observations using NASA's Hubble Space Telescope, as well as numerous ground-based telescopes, including the European Southern Observatory VLT, or Very Large Telescope, in Chile, and the CSIRO's Australia Telescope Compact Array at Narrabri. The explosion, located in a distant galaxy some 4 billion light-years away, was first detected in 2015 by ASASSN, the all-sky automated survey for supernovae. It was so bright, scientists originally categorized it as a very rare superluminous supernova, the cataclysmic death of an unusually massive star at the end of its life in a thermonuclear or Type II supernovae. Only a dozen or so of these so-called superluminous supernovae have ever been detected, and this one was at least twice as bright as the previous brightest supernova ever seen. In fact, at its peak, ASASSN 15LH was an amazing 20 times brighter than the total light output of the entire Milky Way galaxy. The problem is there are a number of things about this apparently record-breaking event which, when you looked at it carefully, just didn't really add up. In particular, the data obtained during the 10 months of follow-up observations revealed that the blast actually went through 3 distinct phases over that time period. Instead of a single peak in luminosity followed by a gradual dimming down, with maybe a couple of plateaus as different elements began fusing, astronomers observed a re-brightening in the ultraviolet as well as a temperature increase, something which more closely resembles what would be expected in a tidal disruption event rather than a superluminous supernovae. The event was also unusual in that it occurred in a giant old red galaxy. Superluminous supernova explosions usually occur in blue star-forming dwarf galaxies. Finally, the explosion appears to have taken place near the center of the host galaxy, the very place where supermassive black holes would most likely reside. The authors have therefore concluded that this explosion is unlikely to involve an extraordinarily bright supernovae. Instead, the findings appear to point to an even rarer occurrence known as a tidal disruption event, something which so far has only ever been observed about 10 times. Tidal disruption events are caused by a rapidly spinning supermassive black hole destroying a low-mass star. In this scenario, the extreme gravitational forces of the supermassive black hole, which is located near the center of the host galaxy, have literally ripped apart a sun-like star that just happened to wander too close. In the process, the star was spaghettified, stretched, crushed, and pulled apart all at the same time, generating powerful shockwaves and intense energy from the colliding stellar debris churning around in the accretion disk of material before it passes the black hole's event horizon and falls forever into the singularity. This series of events gave the appearance of an extremely bright supernova explosion, even though the star itself would never have become a Type II supernovae on its own, as it simply didn't have enough mass. The mass of the host galaxy implies that the supermassive black hole at its center has a mass of at least 100 million times that of our Sun. Now, interestingly, a black hole of this mass would normally be expected to be unable to disrupt a star far beyond its event horizon, the boundary within which nothing is able to escape its gravitational pull. However, if the black hole is of a particular kind that happens to be extremely rapidly spinning, what astronomers refer to as a Kerr black hole, then the situation changes and this limit no longer applies. Instead, the spin of the black hole is literally causing the very fabric of space-time in the black hole's vicinity to rotate with the black hole's spin through a process called frame dragging. Black holes are thought to possess three primary properties: their mass, their spin or angular momentum, and their charge. However, Kerr black holes only possess mass and angular momentum. There is no electrical charge. For a long time now, Kerr black holes were thought of probably being the most common type of stellar mass black hole in nature. That's because the massive stars from which they typically form possess rotation but no overall charge before they collapse at the end of their lives to form a singularity. By the principle of conservation of angular momentum, much of this spin is then retained by the black hole following the star's ultimate collapse. By the way, Kerr black holes are named after the New Zealand mathematician Roy Kerr. In 1963, he became the first person to solve the field equations for Albert Einstein's general theory of relativity for this kind of situation. One of the ASASSN 15 L8 study's authors, Associate Professor James Miller-Jones from John Curtin University, says ASASSN 15 LH was always a somewhat puzzling event, but one which is allowing scientists to now probe some of the fundamental basics of physics.
So this was an extremely luminous optical transient that was detected in June of last year. It's in a galaxy at a redshift of 0.2, which means that it's about 1,200 megaparsecs away. So it's about 4
billion light years.
So this was extremely bright, and it was followed up as any bright flashes of light tend to be. So there are a lot of surveys that scan the sky every night to look for new explosive events going off, because they're great laboratories for probing high-energy astrophysics and looking at fundamental physics in regimes of very strong energy, very strong gravitational fields and so on. And this object was somewhat puzzling, so it was followed with a lot of telescopes after its discovery, and it was originally interpreted as the brightest ever of a class of events called superluminous supernovae. So a supernova is something that forms during the death of a very massive star. So when a massive star runs out of nuclear fuel, it can no longer generate energy to support itself against its own gravity, and then it collapses. And that collapse makes the star get denser and denser, and eventually it gets so dense that it prevents any radiation or neutrinos from getting out, and they get trapped and eventually then blow away the outer envelope of the star, leaving behind a neutron star at the center, or possibly, if the star's massive enough, then maybe a black hole. Anyway, so that's what
This is a core collapse supernova.
That's right. So it's produced by the death of a very massive star. In recent years, we've detected a number of these sort of superluminous supernovae that are brighter than we would expect. So supernovae have an energy budget, just like anything else. There's only a certain amount of energy that can be produced by that stellar collapse. And yet the amount of radiation that we see from this class of superluminous supernovae is more than is predicted by our standard models for what these supernovae should be. There's only a handful of these things known, maybe a dozen or so. So when it was first proposed that this was a superluminous supernova, and a very bright one at that, this was very interesting. A lot of people jumped on it, and so it got an awful lot of observations taken to try and figure out exactly what was going on. So if this were the case, it would exceed the energy budget for these things by a factor of a few. And so we weren't sure how you would power a superluminous supernova with this much energy coming out of it. And so that required revising certain theoretical models. However, following all of the monitoring that was going on, people were taking optical spectra, looking in the ultraviolet as well, looking in the radio and the X-ray bands, just to glean as much information about this event as we could. And our team, as well as studying a lot of the same data that have been taken by many of these other teams, we actually came up with a slightly different interpretation for what this event could be. And due to the behavior of the source, we thought that instead of being a supernova, so formed from the core collapse of a massive star, we thought that rather this actually had the signatures of what we call a tidal disruption flare.
That's pretty exciting, isn't it?
Very exciting, and it's particularly exciting because this particular event, it couldn't be a normal tidal disruption flare. So when a star wanders too close to a black hole, it gets shredded apart, and the debris from what's left of the star falls in towards the black hole and creates a very energetic flash of radiation. This could not be explained by a normal tidal disruption event from a normal stationary black hole. And the only way that this event could be explained as a tidal disruption is if the black hole is spinning very rapidly. So black holes have three main properties. They have mass, charge, which we think is zero for any astrophysically sized black hole, and spin. So they can be rotating. And if they're rotating, they are dragging space and time around with them. And that affects how they disrupt the star when it wanders too close. And what it means is that instead of swallowing smaller stars whole, which would be the case for a black hole of the mass that we know to exist in this galaxy, it can actually disrupt them before they reach the event horizon, so that we can actually see the after effects of the star being shredded rather than all of this happening once it's fallen through the event horizon. We can never get any information out. So it's very exciting, if this interpretation is correct, because it means that we know that the black hole is spinning, and this is a very nice way of probing the distribution of black hole spins from some of the most massive black holes in the universe. Interesting from a techniques perspective as well as from explaining this very intriguing event.
To put this in layman's terms, what we possibly may have witnessed is the black hole spinning so rapidly that it's frame dragging the fabric of space-time near it.
So absolutely, it's dragging the space and time around with it. A star will be torn apart if it gets too close to a black hole, whether it's spinning or not. So the tidal forces on the star, so they're pulling the near side of the star towards the black hole much more strongly than they're pulling the far side of the star. And that means that the star gets basically stretched out into a long stream of debris.
Yeah, it's like a Roche limit.
Gets shredded, basically. Yeah. So that will happen whether the black hole is spinning or not. What the frame dragging and the black hole spin does is it affects exactly how that spaghettification, if you like, happens, how that star gets ripped apart. And it means that you can rip apart a star that would usually, for a non-spinning black hole, just fall straight through the event horizon before it gets destroyed. In this case, because the black hole is spinning, the change in the space-time metric that you have there means that the star gets ripped apart outside the event horizon, and then we actually see this event.
And there are a number of little clues you had for this too, weren't there? One, this super luminous object, this what we think now is a star being destroyed by a black hole in this tidal disruption event. This happened near the very center of this galaxy. And this galaxy is not the sort of galaxy that normally has lots of supernova activity going on in the first place. It's a very old, large galaxy.
That's right. So this galaxy is something that we call a red and dead galaxy. The dominant population of stars is something like 4 billion years old. So it's a pretty old galaxy. There hasn't been very much star formation in that galaxy for some time now. And in fact, we can put a limit on the rate at which that galaxy is forming stars, and it's very, very low. The reason this is significant is because these supernovae have to form from the deaths of massive stars. So you need massive stars in the galaxy in order to do that. Massive stars don't live for very long.
The James Dean effect, live fast and die young.
Absolutely, absolutely. They've got to go through their nuclear fuel much faster than a star like our sun. And so they die within a few tens of millions of years. And so given that this galaxy has not been forming stars for a long period of time, we don't expect it to have the massive stars that should produce a supernova of this type. However, we do expect it to have a significant population of stars in the nucleus of the galaxy that could wander too close to the black hole and get pulled apart.
And this is also a great triumph for the way the whole thing was studied and observed, because a whole bunch of different telescopes around the world, and Hubble in space as well, were all involved.
Absolutely. I mean, any time one of these exciting events is detected, people jump on it, because we want to probe new extreme events. We want to probe interesting new physics that we haven't uncovered before. And these kinds of events are the ways that we can do that. So it provides a fantastic laboratory into unexplored physics for us. So anyone with an interest in this science will try and use whatever telescopes they can get their hands on to take a look and figure it out. And often it takes quite some time before the community reaches a consensus as to what the event could be. But that's the wonderful thing about the way science works. You have different groups forming one hypothesis to explain an event that we see, other groups forming a different hypothesis, and then with such a wealth of data, we can rigorously test all of those different hypotheses and see which one seems to be to best explain the observation. And that's the way that we hone in on the scientific truth, and it's just a really nice way of how this happens. Now, it may be that we haven't seen the end of this story yet. We have yet to see the transient, the explosion fade away, and when it does, that will give us some much better constraints on the background emission from the galaxy, and that can provide some other crucial information. However, our team strongly believe that, weighing up all the evidence we have, we think that this has some of the signatures of one of these tidal disruption events. So we're fairly confident in our interpretation, but of course we'll see what all the new data show.
Was the light curve a bit of a giveaway because the way it was bright, then went down, then went bright again? It's a bit different to what you'd normally expect in any type of supernovae.
Absolutely. So for a supernova, you get one injection of energy. So the explosion that blows the outer layers of the star out into interstellar space, that should expand as the outer layers of the star move out through interstellar space. They get bigger and bigger, and so there's a bigger surface to provide radiation. So it gets brighter for a while, and then eventually it starts to cool, and it gets fainter. What you don't expect is a second injection of energy that can then make the light curve increase again, so make the event get brighter. Whereas this particular event, what we saw was that after about 2 months of the brightness decaying, it started to increase again, and it increased fairly significantly. And that was a bit of a giveaway that something strange was going on. And that was also tied in with some strange features that we saw in the optical spectra of the event. We couldn't explain this. The features that we saw in the spectra didn't seem to be too similar to a number of other supernovae, whereas there were some similarities with other tidal disruption flares that we'd seen in the past. Neither of the explanations can fit absolutely every piece of data we have, so we think that certainly there are still some theoretical pieces of the puzzle that are missing, and obviously we're working hard to try and figure out what those are, and hence that's the reason we'd love to take a little bit more data to really pull apart exactly what's going on. But we think at the moment there are certainly sufficient indications that on the balance of probabilities we think this was a tidal disruption flare.
As the star was being pulled apart, does it get pulled apart just as you would with a Roche event whereby just one side gets pulled apart and before the other side? Or is it sort of pulled apart where the outer surfaces get ripped off first and then the core is exposed and then that gets ripped off? Do we know anything about that yet?
So obviously we've never been close enough to directly resolve one of these events with our telescopes, but we can simulate what would go on. We have a very good understanding of how general relativity works, so we can understand what gravity would do to a star. So what we think happens is that as the star approaches the black hole, probably on a fairly elliptical orbit, it will get basically elongated to some extent, and some of those outer layers, as you say, get ripped off, and then it will come back around again on a second pass towards the pericenter, the closest passage to the black hole. And at that point, it would get really just strung out into a big long stream of gas. So it doesn't all happen at once. It's a gradual process over a couple of orbits, but it's not the same gradual process as a Roche lobe overflow that you would get, say, when in an X-ray binary system, when a stellar mass black holes are, pulling off the outer layers of a more normal star that it's in orbit with. It's a much more cataclysmic event than that. Yeah.
Fascinating story, isn't it?
Yeah, I mean it's amazing what's out there, and we would absolutely love to be able to see all of this with even higher angular resolution and get even better data on it. The more we look, and the more sensitive our telescopes become, the more unexpected phenomena that we find, and that's one of the wonders of astrophysics. Nature can do things that we haven't even thought of, and it's wonderful to be able to explore that.
The other significant thing is a tidal disruption event's only ever been observed about 10 times. So this is still a fairly unique event.
Yes, indeed. So as I was saying, both classes of events groups have suggested this could be. So either the superluminous supernova or the tidal disruption flares. They're both fairly rare classes of events, and we don't know too many of them, which is why there's so much confusion. We don't know exactly the whole range of behaviors that either class can show. Now, what's very exciting is, in the coming years, as new telescopes come online, things like the Large Synoptic Survey Telescope, LSST, that will be built over the coming years, that will scan the sky to a very sensitive depth every night or every few nights. That is expected to uncover way more of these things than the current surveys. Just that advance in instrumentation means that we will be able to push fainter, push to wider areas and detect rarer events than we can now. And so the coming years should be an absolute boon for this field of explosive transient events, looking at some of the biggest bangs in the universe.
That's James Miller-Jones from John Curtin University in Perth. You're listening to SpaceTime with Stuart Gary. NASA's OSIRIS-REx mission is about to begin a search for possible Earth Trojan asteroids. OSIRIS-REx is on a 2-year flight to rendezvous with the asteroid Bennu. However, during mid-February 2017, the spacecraft will be ideally positioned to undertake a survey of Earth's L4 Lagrangian position, which could contain asteroids known as Trojans. Lagrangian points are a series of 5 stable positions in an orbital configuration between two bodies in space, where a small object only being influenced by gravity can maintain a stable position relative to the two larger bodies. Now, in the case of a planet such as the Earth, the Lagrangian points are located where the gravitational pull between the Earth and the Sun balance each other out, thereby allowing an object in one of these locations to permanently remain in that position. The L1 position is in a direct line between the Earth and the Sun, and any object in that position will remain there in relation to the Earth as it orbits the Sun. Next comes the L2 position. It's on the directly opposite side of the Earth from the Sun. The L3 position is on the directly opposite side of Earth's orbit around the Sun. In other words, it's where the Earth will be in 6 months' time. Finally, and this is what's relative to the Trojan study, there are the L4 and L5 positions. These are located 60 degrees directly in front and behind the Earth's orbital path as the planet goes around the Sun. Occasionally, asteroids fall into these L4 and L5 positions, in front or behind a planet as it orbits the Sun. Because they constantly lead or follow in the same orbit, they become long-term travelling companions to the planets, but never collide with their companion planet. The term Trojan asteroid was established when it was decided to name Jupiter's companion asteroids after warriors of the Trojan War in Greek mythology. At the moment, there are 6 planets in our solar system known to harbour Trojan asteroids: Jupiter, Neptune, Mars, Venus, Uranus, and the Earth. Although more than 6,000 Trojan asteroids are known to be orbiting along with Jupiter, astronomers have so far only discovered one single Earth Trojan. Named 2010 KT7, it was identified by NASA's NEOWISE project back in 2010. Astronomers believe there should be lots more Trojans orbiting the Earth, but these asteroids are difficult to detect because firstly they're small, and secondly, from a point of view on Earth, they appear close to the Sun. However, in mid-February 2017, the OSIRIS-REx spacecraft will be ideally positioned to undertake a survey of the stable L4 point in front of Earth. So between February the 9th and February 20th, the NASA spacecraft will activate its onboard camera suite and commence a search for Earth Trojan asteroids. Over 12 days, the OSIRIS-REx Earth Trojan asteroid search will employ the spacecraft's MapCam imager to methodically scan the space where Earth Trojans are expected to exist. Many of the campaign's observations will closely resemble MapCam's planned activities during its upcoming search in 2 years' time of small rocks orbiting the asteroid Bennu. While the likelihood of finding small rocks which could threaten the spacecraft orbiting around Bennu is low, the Trojan asteroid search nevertheless serves as an early rehearsal for this critical safety check, as well as for the mission's primary science operations. OSIRIS-REx principal investigator Professor Dante Loretta from the University of Arizona says the Earth Trojan asteroid search provides a substantial advantage for the OSIRIS-REx mission. Not only does it give scientists the opportunity to discover new members of an asteroid class, but more importantly, it allows them to practice critical mission operations in advance of the probe's arrival at Bennu, which ultimately reduces mission risk. OSIRIS-REx is NASA's first sample return mission to an asteroid. The billion-dollar Origin Spectral Interpretation, Resource Identification, Security Regolith Explorer, or OSIRIS-REx for short, launched from the Cape Canaveral Air Force Base in Florida on an Atlas V rocket on September 8, 2016. Its mission is to study the carbonaceous asteroid 101955 Bennu, which is an Apollo group near-Earth asteroid, originally discovered by the Liner project on September 11, 1999. The mission's important because Bennu is a potential Earth impactor, with a 1 in 2700 chance of hitting the Earth sometime in the next century. The quarter-of-a-kilometre-wide asteroid is named after the Egyptian mythical bird and deity Bennu, which typically is depicted as a heron. If all goes to plan, in 2023 OSIRIS-REx will return to Earth, carrying up to 2 kilograms of asteroid samples. The material it contains will enable scientists to learn more about the formation and evolution of our solar system 4.6 billion years ago. It'll also provide new clues about the initial stages of planetary formation and the source of organic compounds that led to the formation of life on Earth. You're listening to SpaceTime with Stuart Gary. India has launched a new Earth imaging satellite to round off the subcontinent's busiest year so far for space missions. The PSLV, or Polar Satellite Launch Vehicle, blasted off from the Satish Dhawan Space Centre on Shrikota Island on the Bay of Bengal coast, carrying the ResourceSat 2A into orbit.
5, 4, 3, 2,
RCT
1,
ignition.
0, plus 1, plus 2, plus 3, plus 4, plus
Yes,
5,
we-
plus 6,
So vehicle
7,
lift-off normal
8,
with the ignition of
9,
4 solid
plus 10
strap-ons
seconds.
and the core stage.
auto tracking,
Vehicle is majestically
Plus 15
going through the
seconds.
atmosphere, 17 seconds into the
plus
flight
20
now.
seconds,
As I mentioned, this little overcast condition, little cloudy
plus 25
outside.
seconds,
So we're not exactly able to see the vehicle. Is the vehicle at 20 seconds
plus
into the
20
flight.
seconds,
And we heard the announcement, the air lift
Plus
strap-on
25
also has
seconds.
been ignited at a specified time of around 25 seconds. So now we have
Plus
the
40
vehicle with
seconds.
6 solid strap-ons and the core motor going through the atmosphere.
plus 45
Presently we are
seconds,
at 45 seconds and the altitude is
Plus
around
50
5
seconds.
kilometers, velocity of around
plus 55
is
seconds,
nearing 1 kilometer per second velocity. So
Plus
we have
1
at
minute.
70 seconds the separation of the ground lead strap-on, which was ignited along with the core solid motor.
For this mission, the PSLV's core stage used a single S138 solid rocket motor combined with 6 strap-on S12 solid rocket boosters, which have a 70-second burn time. 4 of those strap-on SRBs are ignited at launch, while the remaining 2 are airlit 25 seconds after liftoff.
We're just awaiting for the announcement for the ground lead strap-on has been separated at 70 seconds.
First stage performance normal.
And at 90 seconds, we will have the separation of the remaining 2 air lead strap-ons, which were
Plus 1
ignited at
minute, 30
25
seconds.
seconds into the flight.
under my voice,
Air lead strap-on separated.
Yes, air lead strap-on has been separated, and we will have the separation of the first stage happening at 110 seconds, when the vehicle altitude will be around 110 kilometers.
First stage separation then occurs 1 minute and 50 seconds after launch.
So right now we are at 71 kilometers, so 122 seconds now, 94.8 kilometers.
Second stage performance normal.
So first stage separated 110 seconds, and the second stage is ignited, and the second stage performance is normal.
The liquid-fueled second stage Vickers engine then ignites its mixture of hydrazine hydrate and unsymmetrical dimethylhydrazine, oxidized by dinitrogen tetroxide for a 2.5 minute burn. Once that's expended and the second stage is jettisoned, the PSLV's third stage is ignited, which also uses a solid rocket engine, burning for 70 seconds. Interestingly, once third stage engine cutout's achieved, it remains attached to the stack during a coasting phase until stage separation some 8 minutes and 42 seconds after launch, following which the fourth stage, which is liquid-fueled, is then ignited. The PSLV fourth stage uses a monomethylhydrazine propellant with a mixed oxides of nitrogen or MON oxidizer. It burns for over 8 minutes to place the spacecraft into a circular 827 kilometer high deployment orbit, with payload separation occurring 47 seconds later. The 1,235 kilogram ResourceSat 2A is a remote sensing satellite designed to monitor natural resources for the next 5 years from what will be a circular sun-synchronous 817 kilometer high orbit. It will replace the original 5.5-year-old ResourceSat 2 spacecraft. And like its predecessor, ResourceSat 2A carries a linear imaging self-scanner equipped with a 5.8 meter resolution visible and near-infrared camera for high-resolution imaging. It also carries a medium-resolution camera capable of imaging resolutions of 23.5 meters, and a wide-field sensor which can image a 740 kilometer wide slice of the planet's surface at low resolutions. The 3 multispectral cameras can operate in green, red and near-infrared bands, while the medium and wide-field sensors can also operate in shortwave infrared. This flight was the 7th this year for the Indian Space Research Organisation, the most amount of launches conducted in a single year by the ISRO. 6 of those launches used the nation's PSLV workhorse, while 1 mission used the larger GSLV or Geosynchronous Launch Vehicle, which is designed to place bigger payloads into geostationary orbits. You're listening to SpaceTime. I'm Stuart Gary. And just before we go, a quick reminder that at 21:44 Australian Eastern Daylight Time this evening, Wednesday, December 21st, the Sun will reach zenith, appearing to be directly over the Tropic of Capricorn. In other words, it's the December solstice. In the United States and most areas of the Northern Hemisphere, the winter solstice marks the first day of winter. The good news is that from now on the days will start to get longer again. Here, south of the equator, Summer has now well and truly arrived, and the days will sadly start to get shorter. The seasons are governed by the tilt of Earth's axis as it journeys around the Sun in a year. On the day of the December solstice, the Earth's south pole is tilted towards the Sun. So, when the Earth's south pole is tilted towards the Sun, the southern hemisphere experiences summer. 6 months later, when the south pole's tilted away from the Sun, it's the southern hemisphere winter. In between these, we have the autumn and spring equinox. The Earth's closest orbital position to the Sun, perihelion, occurs about 2 weeks after the December solstice, and it's furthest from the Sun at aphelion, which, as you'd expect, is about 2 weeks after the June solstice. But temperatures on Earth aren't determined by Earth's orbital distance from the Sun, but rather the angle of the Sun's rays striking the Earth. So in summer, the Sun is high in the sky, and the rays hit the Earth at a steep angle. While in winter, the Sun's lower in the sky, and so the rays strike the Earth at a shallow angle. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.